Okay, so Unit 6, this is going to be a sneak preview all about Unit 6, and it's all about infinite series, which is very weird. It seems like it's not important. To a lot of majors, it's really not important. It's one of those weed out classes you have to take, topics that we have to take to get whatever degree you're going for. But it is very interesting. It's a little bit more complicated than stuff you've seen before, and you really have to know your algebra for this. But we're doing infinite series next until the rest of the semester. All right, so in calc so far, we've done slope of a point. This is derivative. So finding the slope of a point, that's derivative. And you need the limit because we're approaching one point infinitely close on both sides. So we need limits for that. We did area of a weird shape, and you're basically just adding up all the little rectangles. If you remember those rectangles, the infinitely many that are infinitely thin, and you're adding them across. Hold on, I think someone just joined. Yes, admit. Okay, sorry. So we needed limits for that because you're adding infinitely many rectangles that are infinitely thin for these. So you may be thinking, well, what's that to do with infinite series? Well, there's 4 big ideas in calc, but we've only covered the first 3. So we covered limits. You need limits for derivatives. You need limits for integrals, but you also need limits and everything else here for infinite series. And what's an infinite series? Well, infinite series is basically when you're adding infinitely many things. Okay, so you have this sigma here. The sigma means sum. Again, this is a sneak preview. Don't write this down. We're going to go over in more detail about this later. But this sigma, this fancy weird E shape, means you're adding up. K is just whatever letter. Usually it's an N. In the book, you'll see N. I use N a lot too. I think this is the only time I use a K. But you're adding up infinitely many things. So this is a 1, and then it's going to infinity. So, and it's counting by ones. So 1, 2, 3, 4. So K is 1, K is 2, K is 3, all the way to infinity. So then it's A sub K. So this is equal to, when you're adding up A sub 1 plus A sub 2, because 2 is the next number, plus 3, plus, and then it's just dot, dot, dot. That means it's going to infinity. That's what makes it an infinite series. So a series is when you're adding up a bunch of stuff. They should just call it an infinite sum, but they call it series. But you're just adding up something infinitely many times, okay? Which has huge implications. It's got crazy, crazy amounts of application, and as you'll see as we go through all this. But you have to understand an infinite series is just adding up a bunch of stuff infinitely many times, okay? So here's an example of a problem. Again, don't write this down. We're going to go in more detail. But say I had the sum, and n is equal to 1, and we're going to infinity. And you don't need the limit on this, which is really weird. You'll see the infinity up here. I know for integrals, the improper integrals, you're not supposed to write infinity up there, but for these you do. It doesn't matter. I counted either way. So you're going to infinity here, and it's 1 over 2n. Okay, and you're putting 1 in, so it's 1 over 2 to the 1, so it's 1/2, and then you put in 2. So it's 1 over 2 squared is 4. 1 over 2 to the 3. 1 over 2 to the 4, and you're adding this up forever. Okay. Now, you might think, is this just infinity because you're adding up infinitely many things? Does anyone know what the answer to this is? This is kind of a weird answer.
Is it just 0? Is it getting closer?
It is getting closer to 0. So you're absolutely right on that. I'm just seeing if anyone chimed in here. It is getting infinitely closer to 0, like each sum is. But the reason why it wouldn't be 0 is because you already have a 1/2 here, and you're never subtracting off. So you're never going to get lower than a 1/2. This is very, very, very complicated. This is very, very weird to picture in your head. And the only way that I can think of to have this make sense, because if you're adding infinitely many things, is to just give a hint. Okay, so here's a hint right here. You have this square, and I just drew everything out. Actually, I just stole this from the internet, but it's 1/2 here, and then 1/4 here, 1/8 here, 1/16, and so on. So based on this graph right here, and it goes to infinity, but obviously we can't draw infinity in real life. Based on this picture right here, what would the answer be? This is still not easy, but anyone have any ideas? It's 1, which is really crazy to think about. This ends up being 1, even though you're adding up infinitely many things. But if you think about it, you can fit it geometrically. This is a geometric series. We're going to talk about that in a little bit. But you can geometrically fit it into a shape like this because, as you can see right here. So, and again, this would be 1/32 and 1/64 and 1/28 and so on. But it actually works geometrically, which is crazy. But that is 1. Very good. Okay, what about this one? Okay, now it's 1 over n. So n is 1 to infinity. So it's 1 over 1, 1 over 2, 1 over 3, 1 over 4, and so on. Does anybody have any ideas on that? It's okay if you don't. This is very weird. Because we're gonna go over this and you'll figure it out in a little bit. All right, cool. Let's keep going. All right, what about, oops, someone wrote it in. I think they know the answer. 2. Okay. I don't want to say you're close because you're really not. But you'd think that it would be some value because the 1 over n is going infinitesimally closer to 0 as you're adding more and more up. It's a really weird answer. That's why I put it in there. So it's not intuitive at all. You can't just think in your head and go, oh, that makes sense. It's this. But we'll see in a little bit. Okay, this one. This is called an alternating series. It's called alternating because the sign alternates. If you notice, it's +1, then -1, +1, -1, +1, and so on. And the way to draw or to write an alternating series, it looks like this. It's -1 to the n. Okay, so anytime you see this, I always it's not, you're not supposed to call it this because it's not a real term, but I just call it the alternator. This is what causes this to alternate here. Okay, and we're going to go over this more detail again because I can't really write on this, but the if n is 0, then it's -1 to the 0. Well, anything to the 0 power except for 0 is 1. So when you plug 0 in here, you get a +1. By the way, I started 1 here. If you notice the other ones, I start at 1. I can start at anything I want. Usually you're going to see a 1 or a 0. This one was 1, this one was 1, this one was 0. It doesn't matter. Okay, it'll make sense as we go. But if you plug 0 in here, you get a 1. Now, if you plug 1 in here, you have -1 to the first power is -1. So you have this -1 here. Now we're on 2, so it's 0, 1, 2. So if you put n as 2, it's -1 squared, that's +1. So as you can see, every single even, it's going to be +1. Every single even value of n is +1. Every odd is a negative. So it alternates back and forth over and over again. Does anybody know what this answer is? There's basically 3 possible answers for it. Any thoughts? Okay, we're going to go over it in a little bit. That's fine. Okay, what about this one? Holy moly. Okay, now this is an alternating series again, only this time I have that 1 over n. I have 1 over n plus 1 to make up for the fact that I started 0 here. So I have the alternator here. Remember, anytime you see this alternator, it means it's going to go minus, plus, minus, plus. Okay, that's what this means. Abstract away the details of it. Just think of it as an alternator. It switches the sign. Here, it's 1 over n plus 1. I'm starting at 0, though, so if you put 0 in here, it's 1 over 1. So you have 1 over 1. Then when you plug in 2, it's -1 squared. Oh, I'm sorry, 1. Then it's 0. 0 to 1. If you plug in 1 here, you get -1, so it's going to have a negative sign. And then it's 1 over 2. Okay, so it's 1 over 1 minus 1 over 2 plus 1 over 3 minus 1 over 4. And I always do 4s generally because after 4 you can see the pattern. So that's why I did this. You could keep your answer like this though if you wanted as well. This is an alternating series. I doubt anyone knows this one. This one's this is probably the most non-intuitive one. Okay. What about this one? All I did for this next one is I put a 2 in front of this n plus 1. So now it's 1 over 1, 1 over 3, 1 over 5. It's every odd because 2n plus 1 is the odd for each of these. That one, again, is very non-intuitive. This is meant to be like an attention getter. We're going to go over this like literally right now. All right, so this first one, that first one I did where it was 1 over 2 to the n with the square, it is equal to 1. Okay, if you add this up, it ends up being equal to 1. And you can also test that on your calculator if you want. Here, let's go to, oops, I didn't want to do that. Hold on. Just want to go to my calculator. Okay, you can do this on your calculator. Actually, take your calculator out because this is fun to show. Hit math and then press up. And you want to go to where it says summation, so 0, so math 0. If you have an older calculator, I don't think you have this. So if you have an older calculator, I apologize. But what we're going to do is you won't be able to do on your calculator. All right, so you have this, and then we're going to do alpha n, which is the log button. So you have an n in there. Let's do this so you can actually see what buttons I'm pressing. And we are going from, what was it? I think we started at 0. Yeah. And we're going to infinity. I'm just going to put 10 in here for now. Okay. And then here, I'm going to do alpha y equals to get the fraction. And then I'm going to do 1 over 2 to the n. So something like that. Okay, and then you hit enter. And you end up with something like that, which is not very interesting at all. Hold on. I want it to be a decimal. Oh, here, I'll just force it. Hold on. Okay, so you get 1 point. Oops, I was supposed to start at 1. I didn't even do this right. I was supposed to start at 1 here. Hold on. Let's just change that to a 1. That's why I ended up with 1 more than I'm supposed to get. Hold on. Jeez, all right. This is not, okay. Here we go. Okay, so here, and then I'm gonna force decimal on this. So I'm gonna force it to be a decimal, and you can see 0.99. Okay, that's just for 10. If I rewrote that 10 to maybe be 100. Now this does take a while because what your calculator is actually doing is adding up all these little things. Your calculator can only add, it can only count really, I should say. You plug that in there. It actually, yeah, it's going to round it off to 1. It actually ran out of memory. That's why it did that. It's probably 0.999 repeating, but you can do these in your calculator using that math 0. I'm just showing you this just in case you didn't believe me with the other thing. Hold on. Where is the... All right, so anyway, that proves that it's 1. Okay, this one is really crazy, but it's actually infinity. Okay, the reason why it's infinity, and this is very hard to picture, and I couldn't find the thing online, and it would have taken me forever to draw it. But if you drew every single one of these and made a shape like this one, it would literally spiral. It wouldn't fit into a square like this. It would literally spiral and get bigger and bigger and bigger. It gets bigger and bigger, slower and slower each time, but it still gets bigger forever. So it actually goes to infinity, which is really crazy because you're adding a smaller and smaller value. You think it would go to somewhere, but it doesn't. And this actually plagued mathematicians like through the 16th century a ton. I think it was the 16th century, a ton, because they just didn't understand how it was infinity. I can't picture it in my head. I guess I can kind of think about it geometrically. I'm going to show you other proofs for why it's infinity later on in the course, but this is crazy regardless. And just to kind of put this in perspective, if you wanted to add this up to be 100, just if you wanted to add these all up to get it to 100, you would have to do 10 to the 43rd power up here. So you would have to do 1 with 43 zeros at the end of it. So 1 to 1 with 43 zeros at the end of it, just to get 100. But it still goes to infinity. It's one of the slowest thing that goes to infinity, like one of the slowest sums. I mean, there are slower ones, but it's really crazy, non-intuitive at all, because it's getting smaller and smaller. You think it would go somewhere, but it doesn't. The next one, the alternating series, there's no sum on this, okay? Because if you stopped here, it would be 1. If you stopped after -1, it would be 0, right? And I guess you could maybe even say negative. No, you can never really get to -1 on this because you started positive. We just go 1, 0, 1, 0. It'd be between 1 and 0 the whole time. And some people think, oh, between 1 and 0 is 1/2. Maybe the answer is 1/2. No, it's no sum because it doesn't actually go to one specific value. You can also put this in your calculator if you wanted. This is obviously not. I'm going to do x just so it's easier, so I don't have to hit alpha n. But let's just go to 10 here. And then if I did -1 to the x, make sure your -1 is in parentheses, otherwise it won't work. It says it's 1, but that's just because this is even. Okay, if I did this again and went to like 101, whoops, went to 101, it's going to say 0, right? Either way, if you keep getting bigger and bigger and bigger, it's just going to alternate between 1 and 0. You can't have two answers like that. So, whoops, jeez. So since you can't have two answers, you just say no sum on that. You're never going to get a problem like this anyway. I just wanted to show you that. Again, this is the alternator. If you used it on this is really, really weird. This is the ln. It's 1 over 1 minus 1 over 2 plus 1 over 3 minus 1 over 4. You end up getting ln2, which is really weird to think about. How do you get ln2 out of alternating a harmonic series? The 1 over n, when it goes up by 1 each time, is called a harmonic series. We're going to go over that later. But you end up with a natural log, which is really weird to think about. When you do stuff with infinity, you get weird values like this. The next one that we're going to do, you end up with a 2n plus 1. That's what I put in there. Now, if you just put a 2n plus 1, now you end up with pi over 4. So somehow pi comes out of this, even though these are just regular numbers. If you remember what you're told about pi, it's an irrational number. You can't make it as a fraction for anything. But weirdly, you can make it a fraction if you add infinitely many things. You can get pi out of something. So if I multiply both sides by 4, you would get all of this is equal to pi, right? Because this would just be a 4 on top up here for each of these, and you would end up with pi. So it's really weird to think that you can get pi just by adding things up. This is actually how your calculator gets pi. Not this exact algorithm, but it's counting things up. Moving on. Okay, so the main questions for today anyway is, can ln x be represented as a polynomial? Okay, so we looked at this thing right here. It says ln2. Can I have ln x be a polynomial, like where you're adding up things like this? Can I somehow get it to where ln x works that way? Can other transcendental functions be represented as polynomials? The answer is yes. Both of these are going to be yes. Just a little spoiler alert on that. And the reason why you want a transcendental function to be represented as a polynomial, that's how your calculator works. Because again, calculators can only count. So they can't understand what a unit circle is. They can't understand what the trig is or anything like that, but they can't count. And the easiest way to count is to make something a polynomial. If you don't know what a polynomial is, that's like x squared plus x plus 1. Okay, x to the third minus x squared plus x plus 1. Like any of those where it's an x, just simple x's, and you're adding and subtracting them, that's a polynomial. Polynomials are simpler than ln's. They're simpler than e's. They're simpler than trig functions. And because they're simpler, it's better to have a computer or calculator work with those, with polynomials. So that's why this is important. When this was invented, they didn't know that this was what it's going to be used for, but your calculator that you're using in your hands is based on what we're going to be covering this entire unit, basically. So it says, why is this important? They used math like that. I mean, just to put it in perspective, they used math like this to get to the moon. I mean, this was obviously when they get to the moon, 69 or something like that. They had to use calculators in this way, using the math that we're going over now, even though this stuff was discovered hundreds of years before that. So that's why it's important. Why do we learn it now, even though it's already like baked into the computers? I don't know. A lot of this math is very archaic. It's kind of just tradition of why. Oh, you're an engineer. Oh, you're a scientist. You have to learn this stuff. So I don't know what it's going to be used for beyond that. But again, I view it as kind of like a big weed out class, like weed out section. Like it's just I don't know. So why is it important? That's why it was important. Why it's still important. I don't know. You're still forced to learn it for whatever reason. I'm just a teacher. All right, so 6.1 is all about power series, all about infinite series. We're going to go over what a power series is in a little bit. It's just when there's a power, like second power, third power, fourth power, but we're going to go over that in a little bit. First thing we're going to cover, 6.1.1, is convergent and divergent infinite series. Convergent and divergent should be your review from, I believe you learned it in pre-calc, but you probably forgot it because it was a long time ago. So convergent and divergent, we're going to go over what that means in relation to infinite series for this first section. Basically, we already talked about this. An infinite series is when you're adding up things infinitely. Okay, so when you think infinite series in your head, I want you to think adding up infinitely many things. That's what we're doing. Series is the sum. Okay, if an infinite series converges, that means it actually equals some value. Okay, so if you have an infinite series and you're adding them up and you get to a value, for example, this one right here, if you add all these up and you get to a value, pi over 4 or ln2, these would be considered converging. Okay, this one's considered converging because it went to 1. This one goes to infinity, that diverges. This one has no sum, it diverges. Okay, that's the main thing that you need to know for that. Again, this is just a sneak preview. We're going to go over this in more detail in a little bit, but just know if the series goes to some sum, that's why it's an S here, then it converges. Otherwise, it diverges. Okay, that's the difference between converges and diverges. Diverges, I always think of it like it separates away. It's never going to one specific value. Converges is like coming together. All right. If the infinite series, okay, so if you're adding these all up, if it converges, then the limit as you approach k is going to infinity. The infinitieth term is 0. Okay. So if you look right for this one right here, if you notice it's going closer and closer to 0, as you go. So if it converges, then that's always going to happen. The opposite is not true, though. Okay, if the infinitieth term goes to 0, it doesn't necessarily mean that it converges. It's just if it converges, this goes to 0. Okay, if it diverges, then that infinitieth term is not 0. Okay, and you can kind of imagine that if you were adding up a bunch of ones, just 1 plus 1 plus 1 plus 1 plus 1 plus 1. That's an infinite series. That clearly goes to infinity, and the infinitieth term is 1, and it's not 0, so then it's going to diverge. You have to go to 0 if you're ever planning on converging. Now, some don't, even if you go to 0, some still don't converge. For example, this one. This one goes to 0, but it doesn't converge. It's a weird one. This is a very weird problem. Again, we're going to talk about that later. But just know if it converges, then it goes to 0. If it goes to 0, it doesn't necessarily converge, though. So it works this way, but not backwards. This one works both ways. But we're going to talk about that a little bit. 612 is all about geometric series. It's really about geometric infinite series. I should have wrote that in there. Geometric series is when you have something where it's like, forget this summation notation right now, but it's like a plus a to the r to the 1 plus ar squared plus ar to the 3 plus ar to the 4 plus ar to the 5. That's a geometric series. We're going to go over this in more detail. There's a lot of writing here. I'm going to ignore it for now. And the last thing we're going over is power series, and that's basically just like a geometric series. You're just adding up. If you notice, it's got a constant here. You can have a constant. It doesn't always have to be 1, but it's just c x to the 0 plus c x to the 1 plus c x to the 2 plus c x to the 3 plus c x to the 4 and so on. That's called a power series. Okay, you could have it where it's centered at 0, or you can have a minus a in here, but we're not going to worry about that right now. Just know a power series means it's like the power just keeps going infinitely bigger and bigger each time because n is going to infinity. So that's basically a sneak preview of the entire section of infinite series. Okay, now let's get kind of more into the weeds. But are there any questions before we do that? Okay. Sorry, somebody emailed me. Let's go with the let's go over the notes now. All right. So right here, week 5, it says go over quiz 3. Right here, we went over it briefly. Again, if you want to go over it in more detail, please let me know. The average was pretty high, so that's very good. We already did the overview, so now we're right here with some example problems and going further into the weeds on this stuff, and then we'll still do the practice final problems like normal, and then office hours at the end. I should write that in there. All right, you're probably going to want to write this down now. Okay, I usually view it as if I write it down, like I wrote this down, then you're going to want to write it down too. So if you want to think of it that way. All right, so first thing here, it's an infinite series is, like I already said this before, you're adding up infinitely many things, going from 0 to infinity. You can do 1 to infinity, you can do 2 to infinity, 3 to infinity. It doesn't matter. The main thing is this infinity part. That's what matters. Okay, and you're just adding up across. Okay. Okay, this one, it says, if the infinite series, well, here, I'll wait and just, I want to talk while people are writing. All right. All right, so if the infinite series, remember this means infinity, an infinite series is equal to some value, it converges. You probably really don't need to write that. Well, maybe, yeah, write it down. You have to memorize that. If it's a certain value, then it converges. Otherwise, if it's not a certain value, then it diverges. Okay. That's just the definition of convergence and divergence. Okay. If the series converges, then the infinitieth term, infinitieth is not a term, it's not a thing, I just don't know how else to say this. The term that when you approach infinity, it has to be equal to 0. if it converges. Okay, it's not always true the opposite, meaning you cannot say, this is not going to be accurate, but you cannot say if, oops, should have wrote a limit in there. If the limit as n approaches infinity for the infinitieth term is equal to 0, then the series converges. You can't say that, okay, because it's not true. This is not true. It's called the converse when you write it backwards. The hypothesis and the conclusion. The hypothesis is this if part. The conclusion is the then part. Okay, this is not true. Okay, it's true this way, not the other way. The divergence does work. Okay, the converse is always true. Okay, if the series diverges and the limit is not equal to 0. Okay, or if the limit for the infinitieth term is not equal to 0, then it diverges. This actually works. The other one does not work, again, because you can think about that 1 over n as an example. All right, you will not be given questions on 611. And the reason why is because the main thing of 611 is the definition of converges and diverges. I still give practice problems for it, but you will not see this on a quiz. In fact, your quiz is only really going to have one type of problem on it. There'll probably be like an A, B, and a C, but it's only going to be one problem. You will not have a 611 problem. If you look at the website for 611, you'll notice that the problems are very easy because this is an older topic and it's just not. The main thing for 611, again, is that definition of what is convergence and what is divergence. So if you look at, there's not that many problems. Let's do this. And it just basically goes over the stuff that we went over. Like, is this going to a certain value? Is this going to a certain value? And so on. Is the limit approaching 0 as you get further out? But again, you're not going to see anything like this. So if you do skip it, that's totally fine. The most important thing is 613. Okay. Any questions on 611? Actually, you know what? We should do an example problem. That's a good idea. All right. So let's see here. Let's zoom in. But again, you're not going to see any questions like this. All right. This one right here. Let's do 7 because it talks about everything, every concept that we talked about so far. Well, actually, so did 6, but it doesn't matter. Okay. So for 7, here, let's do this. Paste it in here just so I don't have to bop back and forth each time. Let's blow this up a little bit more. Okay, so this first one is an alternating series. As you can see, in the way you can tell if it's alternating is if it's going plus minus, so and so on. Also, you have to remember that that alternator, again, it's not a real term, but this means alternating in between each one of these. The dot, dot, dot means infinity. Again, so you just imagine that you keep adding. So as you're going to this, you have to think, is the term right here, the infinitieth term, is that ever going to be equal to 0 here? Or is it not going to be equal to 0, I should say? And the answer is no, it's not. It's 1, 2, 3, 4, 5, 6. It's going to go to infinity. It's never going to be equal to 0. So since it's never going to be equal to 0, you would just write diverges. Okay. This one does the same thing. It's never equal to 0. It's just 1, and then it's adding a 0.1 each time, but you're still adding a 1 each time. Like, forget the 0.1 repeating. Forget that. You're still adding 1 plus 1 plus 1. Let's just say we round down on this. 1 plus 1 plus 1. It's still going to be infinity, so that would be diverges. Okay. This one, same thing as number 6. This is diverges. This one is not, because it's geometric. Okay, this one actually does work out to be convergent. Converges. This one right here also converges because this is getting closer and closer to 0, and it's taking up. If you were just trying to draw this, you're trying to write it out, that value for this one right here, it would be 3.5 if you add these two. This one right here, you're adding another 5, but it's 0.05. This one again, and if you notice, that's what you're doing for all of these. Okay, so this is actually, this converges because it's really just 3.5 repeating. So this would be converges as well. This one right here would be diverges because it never does that 0 thing. It's just going to keep bouncing back and forth. The only difference was this was a 1 before with the example we used. But again, it still diverges anyway. Okay. But again, you're not going to see any problems like this. Just because, I don't know, it's just, you don't see any problems like this in a calc class. But you need to know what diverges and converges mean. So that's why this section exists. Are there any questions on what I just went over there? Again, don't worry about the problems. Worry about the definition of converges and diverges. If you understand these definitions, then you'll be able to do these problems. But again, you're not going to see it on a quiz or a test.
Could you repeat how you did number 9 again?
Number 9 is, it's a geometric one. I really shouldn't have put this one in here because it should be in 612. But the base for all of these is 1/2 to the, oh, it's right here. Forget this one. It's, yeah, forget what I just wrote here. This one's 1/2 to the k. It's actually, it's the one where you can actually just, hold on. I went over it.
It's the one that equals 1, right?
Yeah.
Oh,
Yeah, I really shouldn't put it in that one because it makes more sense. It makes more sense as going in 312 or 612. I'm sorry. So let's not worry about that one because we're going to go over it right now for the converges. Kind of do that out of order. Okay, geometric series is whenever you have, I used R in the overview. It doesn't matter. Any letter you use, it doesn't matter. K, N, R, X, it doesn't matter. You will see X mostly, so that's why this says X here. But a geometric series is basically when you have like X to the N here, and it's just going up, the power goes up each time. A is a constant, okay? A lot of times A is 1, but it could be 2, it could be 3, it could be anything. Okay, so forget about what A is, it just distributes to each one of these. But a geometric series is when the power up here grows each time by 1 as you go to infinity. Okay. And we're going to answer that number 9 question while we go over this right here. So we'll answer this question as we go over it. It'll make sense. You'll see, I promise. All right, you're probably going to want to buckle up a little bit on this one because this one gets a little crazy. You don't necessarily need to write all this down. In fact, I probably wouldn't write it down because you can pay attention more if you're watching me do it. You can always write it down later on when watching this video. I also made a video of this on the website. So if you go to geometric series, there's a video here that explains all of what I'm going to do. But it just gets complicated, and you definitely don't have to know it. You have to know the conclusion of it, but you don't need to know the process of where I'm going with this. But I don't know. I think it's cool. So just try to bear with me on this. Again, I wouldn't make sure you understand this definition because you need to be able to look at something and go, oh, it's geometric. Eventually, you will be able to look at number 9 and go, oh, that's geometric. You can see that it's got a power, and the power is going up each time. In this case, it's the K. But this will make sense as we go. All right, here we go. Stop me if you have questions. Don't write this down. I just want your brains for right now. All right, this whole thing right here, if you notice, I just wrote it twice. I think I actually just copied and pasted it. I'm going to say this is equal to S, so I never have to write it again. I'm just going to be lazy on this, okay? I did not come up with this either. This is just genius, the person that came up with this. What I'm going to do is I'm going to take my S, and I'm going to multiply it by X. I'm going to try to color code this as much as possible. Okay, so I'm going to multiply all of this S by X. So it's going to end up being this. It's going to be A times X. So I'm going to it basically just multiplies all of these by X. AX squared. Now, I'm aligning everything up too. So you should see like how it affects each term. Plus dot, dot, dot. Now, if you did AX to the N times X, it would just be AX to the N plus 1. Okay. You can do that because I multiplied it by X. What you can do is you can add the exponents. That should be a review. You should know that you can add the exponents there. Plus dot, dot, dot. Okay, this is equal to X times S. X times S, XS. Okay, this is where it gets crazy. Here we go. Now what I'm going to do, for no particular reason, someone just decided to do this one day. I'm going to take S and I'm going to subtract off XS. Sorry, I'm trying to still do the little color coding thing. I should have done it this way. And a very weird thing happens. Okay, so I'm taking this S here and I'm subtracting it from this. Now it's kind of cool. Okay, this A, there's no A here, so that's when you subtract them, the A is just going to come down. But if you notice, this and this are going to cancel. Okay, because it's S, this is S, minus XS, so that cancels. This is going to cancel with this one. This is going to cancel. Now this is going to cancel with all the dot, 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 because technically there is an AX to the fourth in there. It's just in the dot, dot, dot. Okay, this is also in that dot, 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 because directly after this is this, because this is an N and this is N plus 1. So this one comes after this. Okay, and then so on and so on, everything's going to basically cancel. Okay, well, this one didn't cancel in what we're writing here, so I'm just going to write this in. So it's going to be AX to the N plus 1. So you have something like that. Okay, is everyone with me on how I got that? Okay, now N is still going to infinity, so really I wrote this wrong. Let me move this over really quick. I should have had a limit in there, so that's embarrassing. So the limit as N approaches infinity. Otherwise, I just have an N sitting there coming out of nowhere. That doesn't make any sense. The A is constant. The X and the S are defined. So that's what that is. Okay. Now, a really interesting thing happens. Well, first of all, you should see this is a constant. This is an infinite sum, and this is an infinite sum. Okay, they go to infinity because I just did X times S. X times S is still an infinite series. These are two infinite sums. It's equal to a constant. A is a constant plus this limit right here. Now, what you can do, again, I didn't come up with this, is if this was equal to 0, let's just say this equals 0, which it doesn't yet. We're going to go over that. That means that an infinite series minus another infinite series is equal to a constant. And if it's equal to a constant, that means it converges. Okay, again, kind of weird to think about. We're going to infinity, but somehow we end up with a constant as long as this is equal to 0. So the thing is that you have to know is, when is this equal to 0? And this is equal to 0 if X is less than 1 or if X is greater than -1. I shouldn't say or, I should say and. If X is between -1 and 1, so the interval would be -1 to 1, non-inclusive, so you can't include the 1. This is technically equal to 0. Okay, I'm going to explain why. Let's do that in Desmos. This is getting crazy. I'm sorry. Okay, so say we had, let's do AX to the N plus 1. Oops. Always does that. If something like this. Okay, if A is equal to 1, here, let's just say this is a function. If A is equal to 1, you can see it goes to infinity. Okay, but watch what happens if, or no, forget A, I meant X. Here, hold on. Oh, geez, I did this all messed up. Let's see. Yeah, let's just keep A as 1. N is going to infinity, so that technically is going to do something like that. As you can see, it's still going to infinity. But if you had, here, let's do this. Let's just put a value in. Let's put 2 in. Okay. Here, let's just keep this as 1. Sorry. It's up so you can see it. All right. And let's change the color on this to red. Doesn't matter. Okay. So here it's 2. Now, if you notice, as let's do 1. Doesn't matter. Okay. If N is 0, then it's equal to 2. Okay, because really you're just going to be doing A is 1. Here, let's just get rid of the A so it's less confusing. All right, so you have 2 to the N. Let's forget the plus 1 as well. We don't need that. So we have 2 to the N here. Okay, if N is increasing, watch what happens to this F value here. It's just going to go higher and 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 higher. It's going to go to infinity. Okay, if I kept adding more values here, you can see right here it's going to infinity pretty quickly. Okay. Now watch this. I'm going to change this 2 to a 1/2. Okay, so now it's really here. Let's rewrite this here. Let's get rid of this n. Okay, now that it's 1/2, and by the way, this could be any value. It's always going to be the same just because it's a constant. I just put 1 in there. I could just put 0. It doesn't matter. All right. Now if you notice, here, let's start here. Okay, as n goes to infinity, watch what happens to our value here. What is that getting infinitesimally closer to? Does anybody know? Anybody have any idea?
Negative infinity.
Well, it's not negative, it's positive.
Oh.
So it's not negative infinity. It's not positive infinity either. Does anybody know what this value represents? I mean, you can see it on the graph. Where is it on the graph? Where is that horizontal line? Here, I'll overload the computer. It's 0. Okay. So if you notice, when this was 2, here, let's do this. Let's change this to b for the base. Okay. If it's 1, let's do this. Hold on. If it's 1, that's not going to do anything. If you added it up, it would be infinitely many 1s. But if you did 2, oops, hold on. I got to backtrack this. I'm overloading this thing. Hold on. If it's 1.3, you can see that it's going closer and closer to infinity as we do it. But if you make b anything less than 1, you'll notice it's getting closer and closer to 0. Okay. If the base is between -1 and 1, I'll even go negative on this. Let's do -0.9. It ends up getting closer and closer to 0. But as soon as you get outside of that range, it blows up. Okay. And this isn't even the sum. This is just the value. You're adding up infinitely many of these. Okay. So you're adding up a humongous number plus other humongous numbers. It diverges really quick. Where here, you're adding up numbers that are getting infinitesimally closer. Oops. That are getting infinitesimally closer to 0. Now this overloads because it's negative. If you really think about it, if you wanted to write this number down, it would be at 18739277039, but you have to have 313 zeros here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I mean, you just have to have 300 of these, over 300, to even get to the value. So as you can see, it's 0. It's approaching 0. That's what this is. That's why it's shown here. So the moral of the story is, let's go back to this. I feel like we're getting lost here. If x is between -1 and 1, this is equal to 0, which means that x, let's do a different color. Go back to red. X minus s is equal to a as long as this is true. Okay, this is called the interval of convergence. It's where it's going to be converging. Okay, and it's convergent because this is a constant. But watch this. Now it even gets crazier. This is the last step. You can solve for s here. Okay, I'm going to factor out an s. Okay, and then I'm going to solve for s. And it's going to be equal to a over 1 minus x. Now think about this for a second. You have an infinite series. This is infinite. S is infinite. That's how we defined it up here. Right here, s is infinite. But we made it equal to something that's not infinite. None of this is infinite here. I mean, x has to be between -1 and, -1 and 1 for this to be true. But an infinite series, infinite geometric series, can actually be equal to something that's finite, which is insane to think about. Okay, so what you need to get out of all this is to find the sum of a geometric series. First, you have to see that it's a geometric series. So that's going to be where whenever you have some value, and I don't know why I'm rewriting this. You have some value, and the power is going bigger and bigger each time. Okay, that's a geometric series. When that happens, you have to think, what is the base? So let's go back to number 9. The base of this exponent right here is going to be 1/2 to the n. Okay, or it has 1 over 2 to the k right here. Okay, this 1/2 is between -1 and 1. Okay, between -1 and 1, 1/2 is there. So because of that, it converges. And what does this converge to? Check this out. It's going to converge to 1 over 1 minus 1/2. Okay, this is going to be equal to 1 over negative no, I'm sorry, I ended up at negative 1 over 1/2, which is equal to 2. Okay. Now the reason why it's not actually equal to 2 is because there's not a plus 1 here. So if you subtract off a 1 from here, it ends up being a 1. And that's why when we did that overview problem, it ended up being equal to 1. If you remember, this problem right here ended up being equal to 1. That's because we started at 1 here. The other one I just showed, it starts at 1 over 1, so there's a plus 1. That's why it ends up being a 2. But it ends up being the same thing. Again, the moral of the story is the base has to be between -1 and 1. And if that's true, you can just plug it into this formula right here, and you get the value. Another important thing to note, though, for geometric series is you have to start at 0 with that. That's why this ended up being 2, because it ended up being 1 plus 1/2 plus 1/4 plus 1/8. This extra 1 makes it 1 plus 1. If you remember here, there's no plus 1. It ended up being a 1. This doesn't exist in that first thing that I showed you here, which I really should have made it do it. Oh, I didn't do it because of the picture. The picture would have to have another square here. That's why I didn't do it. But you can kind of get the idea. Okay. So main thing is you need to know this green right here. This is the most important thing. This is home base. This is what we're going to use for 613 to solve any of the problems that we're doing. This is basically it's the conduit to get, it's the conduit to get something that's infinite to be something that's finite. Okay. It's what connects those two things. Okay. Any questions on that? Okay. I'm going to show you this more in Desmos now because this will make more sense, I feel like, if I do. All right, so forget all this. Let's say that our function is going to be equal to a divided by 1 minus x. Okay, and then a can be 1. We'll just make a 1 for now. So you have some function that looks like this. Okay, and again, it's based on this. I just wrote this as f of x because I have to for this calculator. Okay. Now, technically speaking, this should be equal, that f of x should be equal to function g of x, where it is this up here. This ax to the 0 plus ax to the 1 plus ax squared. So I'm going to write that in there. Ax to the 0 plus ax to the 1 plus ax squared. Anyone notice anything happening here? If you don't, just chime in if you figure something out. Ax to the 3rd. Anyone notice anything yet? Okay, well, watch what's happening between -1 and 1. Here, let's zoom in here. Here's -1, here's 1. Watch what happens when you note. Watch what happens when you look through each of these. Ax to the 4th. -1 and 1. What do you notice? All right, everyone's being shy. That's okay. If you notice, it's starting to overlap between -1 and 1. Okay? If you remember when I first started it, it looked like that. It overlapped in one spot. If you keep going, it overlaps more and more between -1 and 1. Okay. Now, why is it not perfectly overlapping between -1 and 1? Does anyone have any thoughts on that? Help me out. Come on, no one knows? Oh, people are writing stuff in here. Okay, the reason why it doesn't overlap is because you're not going to infinity. I stopped at 4. So does that mean if I actually went to infinity, it would overlap more? So what I did is, rather than writing that out, because that was terrible, I made a Python program that basically does all that. And if you run this, you can write exactly how many terms you want. In this case, I want 10. Okay, but 10's not that many. Let's do 50. Okay. Now, imagine writing all this out. It would be an absolute nightmare. So I'm just going to copy all this. Hold on one second. I have to do a little. Okay, and then I can paste this in here. Now it's counting it, so it took a little bit. If you notice, it didn't just show up right away. But if you notice, if I do 50 of them, it's almost perfectly overlapped. Okay, it's thinking. When you do 50 like this, it has to actually count each one of them. But if you notice, -1, it's not very good at -1. So as you get closer to here, it's a little bit off. As you get closer to 1, oh man, I'm going to be zooming out for a while. Hold on. There it is. It's off by a little bit as you get closer to 1. But in between, it's pretty it's a pretty awesome. Hold on, it's thinking. There it is. It's a pretty awesome approximation. And what you can do is check this out. You can do, we're going to do the absolute value just to make it positive of, just do some value. I'll just do C for now, minus G of C, okay? F of X and G of X are supposed to be the same. So if you subtract them off, if you notice this one's undefined because it's 1. But if I did something like, I don't know, 0, the difference between them is nothing. That means if you zoomed in here, it's going to perfectly overlap the whole time. Okay. Now, if I did something like 0.1, there might be a little bit of an error. Okay, because I only went to 50. If you notice, that's a tiny error. Okay, that's 0.0 with 15 zeros, 222. Okay, so it's a very tiny number. Okay, as you get further and further away, the error is going to be more and more. This actually goes. It's counting it, I believe. I might have overloaded it. Let's do 5. Okay, there we go. Okay, it's off by a little bit more. Now, if you did 1, again, it was undefined because you're doing the exact same thing. Actually, you can't plug in 1 to this original because you're dividing by 0 then. 1 minus 1 if you'd be dividing by 0. Let's do 2. It's going to be a humongous number. If you notice, that's diverged. That means the difference between these two is huge. Okay, so if I went to 2, this is going to take forever if I do this. Here's 2 right here, but it goes up. This is going to take forever. It's not gonna show out 2 for a while because like I'm at 200. I need to get to 2.25 with 13 zeros at the end of it. So that's gonna take too long to show you. But if you actually zoomed in around that area, and if you know, yeah, see, it's getting a little weird, a little wonky. But if I did something like 0.9, the error is going to be a little bit more. It's still close to 0, but it's close to 1, so it is a worse approximation. Okay, as you can see, as I go lower, off by less. Okay, and again, I only went to 50. If I went to 100, it would be even better. So long story short, the reason why it's not overlapping perfectly is because I didn't go to infinity. And if you notice, it only works from -1. This is -1 to 1. Okay, the reason why is if it was anything else, it would diverge. If you notice right here, if you do -2, it's off by a lot. Okay, this is where it's supposed to be. This black one goes pretty much up forever, so it would be off by a lot. Long story short. All right, so that's a geometric series. Main thing you need to know is this equation, and it works when x, that base, is between -1 and 1. Okay, and we're going to use this for this next part, representing functions as power series. And if you remember before I said ln x, what if we can make that into a polynomial? That's what we're going to do. We're going to use this right here. We're going to use this to make anything into a power series, to make anything a polynomial, because then you can count it. If you can count it, then the calculator can do it, can use it. Okay, we're going to break here just to see if everyone else is on board, to make sure everyone's on board still. But let's just take 5. I'm just going to be sitting here, so ask questions if you got them. Set timer for 5 minutes.
So was there no examples for 6.1.2?
Yeah, 611 and 612, there's no real examples, but you need you need both of these for these. Okay? If you notice, 613 has this. It has the a over 1 minus x. Okay? You're going to need it for this. You're going to need it for this problem, So you still need 611 and 612, but you're never going to see a question because there's not really any calculus in it, to be honest. Okay. I mean, I guess I can give an easier question to kind of boost people's grades, but it's probably a good idea. But there's nothing like very rigorous with it. But you still need to know what convergence means, what divergence means. That's 611. 612, you need to know this part right here. This is home base. This is our key to unlocking every single other equation that we want. Power series and then this function. There are example problems for 612 if you want to look at them, but if you can do 613, then you're doing 612 just because you're doing 613 because you need this whole thing right here. Any questions before we start? All right. Timer's about to go off. I guess we can just get started here. All right. So again, what I was saying, this is home base. This is what you're going to use. This is what you're going to want to use to make any power series into a function. Another thing I forgot to go over was another factoid is if you can turn something into a power series, then it's a polynomial. You can also find antiderivatives that were normally impossible to find, but you can use series to actually figure out a polynomial. A polynomial has a very easy antiderivative because you would just be using reverse power rule. Okay. Again, polynomial is just when there's x's and the powers are all, oops, there's no x on that one. The powers are all positive. So this is a polynomial. This is a polynomial here. Okay. When it's not a polynomial, it's like when it's something like this. That's not a polynomial. Okay. When it's something like this, that's not a polynomial. That's a transcendental function. Okay, so you want to make things polynomials because if they are, then you can do certain math on them that we normally wouldn't be able to do. Okay. All right, so let's get rid of all that. All right, so the main thing here is we're trying to make a function into a power series. Okay, and it's going to be based off this function, and then it's going to be going into this power series. Okay. Again, this is home base. And if you notice, it says right here, the absolute value is less than 1. This just means this. Okay. If you graph this, it means the same thing. Okay. A lot of times books see it, you'll see it like this because I think it's more concise. Usually I write it like this, though, because why even fiddle with the absolute value? But that's what it is. It means the same thing. That should be a review. Let's go over this. Here we go. So it says write f of x as a power series. So we want to write this thing here as a power series. So step one, none of this is intuitive, by the way, so definitely ask questions if you got them. Step one on this would be to make it look something like this. Okay, that's always step one for any of these problems. Am I on mute still? No, okay, just making sure. That's embarrassing. All right, so I want to make it look like this as much as possible, meaning I need to have a constant on the top, which I do. That's awesome. I need to have a 1, which I do, and I need to have a minus something. It needs to be minus something. Here it's plus. So what we're going to do, and this is where the algebra comes into play, we're going to use some algebra to write this out to be, instead of plus, we're going to make it minus. But because I made this minus, I also have to make this inner part minus as well. So now it's a minus negative x. So everything I just did there is perfectly legal. You still end up with the same thing. I don't have something that's not equal to where I started. Okay. Are there any questions on what I did there? Okay. That's the first step for this. And now we can actually use what I keep saying is home base. We can use this to figure out what this is, because this x got replaced with negative x. Okay, this is our negative x. Okay, so that means this x has to be turned into a negative x. So what we're going to do, I'm going to zoom out a little bit so you can actually see it. Remember, this is home base up here. What we're going to do is we're going to say this is equal to the sum as n goes from 0 to infinity of, now a is 1, so I'm just going to keep the 1 there. I'm not even going to write a 1. That's pointless. But our x is negative x for this new one. Okay. What sometimes I do is I call this an r because it's the rate of the geometric. Okay. That's the r, and then it's r to the n. It doesn't matter. Don't even worry about the r. Forget the r. It's more confusing. So we're going to replace this x with a negative x instead. The a is 1. I'm just going to put the a in there for fun. Again, I really wouldn't. It's kind of a waste of time. And now the x is not x anymore. It's negative x to the n. Okay? You are essentially done now. That's really literally all you needed to do. But you needed to turn this plus x into a minus x. Now, one thing that you'll see people do, I really don't care about this so much, but you'll see them, books usually do this, is they... Actually, let's actually write this down. Forget what I was going to say because it's going to come out what I'm going to do right here. All right, this, if you had to write this out, if you had to expand this, it would be negative x to the 0, because n is 0 first, plus negative x to the 1, plus negative x squared, plus, negative x to the third. Now I have 4 things here, and I usually stop there because you can see the pattern by then. So I'm just going to write plus dot dot dot. Okay, is everyone with me still? I just literally wrote it as a geometric series because I wanted to show you the pattern. This will make more sense as we go. Okay, anything to the 0 power is 1, so I'm just going to put a 1 here. Even though if it's 0, it won't work, but just ignore that for this. Okay, negative x to the 1 power is just minus x. Negative x squared is just x squared. negative x to the third is just negative x to the third. Plus dot, dot, dot. So now you can really see the pattern. It is an alternating series because we have a plus 1 minus x, plus x squared minus x cubed, and so on. It's going to flip-flop each time. So your final answer, what you usually see in books, this is what I was talking about before, what you're usually going to see is they have an right as soon as you see that there's an alternating series, draw the alternator in, write that in. Okay, you can see that it's plus minus, write that in right away. Okay, now ignore the pluses and minuses and just think about what is the x value doing. Well, it's just oops, color. It's just going up by 1, and this is going up by 1 with this right here. So you could just do x to the n. Okay, this is the same answer. This right here is this. Hold on. Let's just circle this. This right here is equal to this right here. Okay, I would accept either of these as answers, but a lot of times you're going to see this in books, and professors usually make you get the negative, the alternator. They like to have that pulled out of there. You could have also factored it out of here as well, because technically with this orange step, you could have done technically negative 1 to the n times x to the n is equal to this part right here, which is what we have right here. You could have done that as well. I do like drawing it out. So you'll notice my answer key, I just draw the first 4 out, and then I try to go to a series from there. It doesn't really matter. So either of those would be the answer. Okay, and it's all based on home base. It's all based on this. This is not called home base. I call it that. It's not a real math term. Okay, obviously. But you have to use this to figure this out. Okay, are there any questions on number 1?
Yeah, maybe this is dumb, but when you rewrote it as the sum of n equals 0 to infinity, where'd you get the 1 from? I know that's a, but how do you know that a is 1?
Because whatever's on top here is your a.
Okay, thank you.
Yeah, and it's awesome that you did that, because like everyone that wrote the feedback say do more examples. The next example, I put a 2 there just on purpose to show you that the a is 2 for the next one. So it's good that you brought that up.
Okay. Awesome.
But yeah, that is a. So yeah. This was the original problem that was on your practice final. I changed the original problem though to have a 3, just because I want to give you a little curveball. But this is an actual quiz-like problem. Like this is shown up on AP tests. So if you're like, oh, this is easy, then great, you're in the right boat here. You're doing well. Okay, but let's keep going. All right, so this next one, now it's 2 over 1 plus x. Now what you can do, and this is going to be completely legal, and this is going to save you a lot of time, and I'm going to allow this on test too. So if you hint, it's going to be on the test too. What you can do is I'm going to pull that 2 out. Still perfectly legal, what we just did. But we know what this answer is already, which is kind of cool. We know what this is. We know it's equal to this. Okay, so if you wanted to, again, you don't have to do this. If you want to go through all the steps, by all means, you can just substitute this in. So now this is going to be equal to 2 times the sum of n going to 0 to infinity, alternator x to the n. This still works, and I would give you full credit for it. Now, if you want to, you can go the long way, and you can do the exact same thing over that we just did here, only this time this 1 becomes a 2. Okay, so now this 1 right here just becomes a 2. You're going to end up with a 2 here, which is what you have here, only the 2's in front. It doesn't really matter if it's in front or inside, because you're just adding things up. You could have even put it over here if you wanted. It doesn't matter. I would count it either way. Some professors are weird, though, and they'll say you have to have it inside the sigma or you have to have it outside of the sigma. It doesn't actually matter. So if you wanted, and you'll see me do this a lot of my answer keys, if there's a constant there, I just pull it out and keep it as a 1 and then just multiply it at the end. Because then I'm just dealing with 1s the whole time. I don't need to worry about that 2 ever. And then this is the answer here. Okay. If you notice, the 2 does not have an n in it because the 2 is constant. So you can't do 2 to the n. 2 to the n would be going to humongous numbers. It'd be 2 to the first, 2 to the second, 2 to the third, 2 to the infinity, which is infinity. So just keep the 2 constant. It's just a regular old 2. Questions on that one? Okay. The next one's even trickier now. Here we go. It's not that much trickier, but it's trickier for sure. We need this to have a 1 on the bottom. There's nothing on the bottom that's a 1, so you have to use algebra again for this. Actually, let's make this a 3 rather than a 1, just so I can show you what I'm talking about. Okay, let's make that a 3, just to make the problem harder. All right, so we're going to do 3 times 1 over x. But home base states that we need a 1 minus on the bottom. We do not have a 1 minus. Does anybody want to help me out with that? How to get a 1 minus there? That has to be there. But it still needs to be equal to 1 over x. That second part right here needs to be 1 over x. Well, we want the 1 to be gone. So it has to be 1 minus 1. Okay. It also needs to be a positive x. Right now we have a minus there. So what you need to do is just put a minus x in there. So now this orange is actually equal to the red. It doesn't look like it. Well, if you work it out, it does. And now we can use home base. Okay. Home base is the geometric series. I got to stop saying that. I do not sound professional. So now we can use this thing right here. A in this case is going to be 3. I don't really need to worry about that for right now. So let's do this like we would do if we did the last couple problems. All right. This right here is going to be that R. Forget the R. I didn't teach it that. The R that I'm talking about comes from the overview. Where's that overview? Right here, because that's how it's defined. Usually in books they use an R. We're using it as an X because we're turning it into a power series, a function into a power series. So that's why that's like that. All right, here we go. Let's do, okay. So this is going to be equal to 3 times, we're going from 0 to infinity, because that's our geometric series sigma that we need. Right up here. All right, our A for this part is just going to be 1 because we took the 3 out, so that's awesome. Now it's x to the n, but that's when it's x. That's when it's x. It's 1 minus x. Here it's 1 minus 1 minus x. So really what you're going to do, is he okay? Sorry, we have a teething baby. So you end up with something like that. And that ends up being your answer, actually. You can't really simplify that or anything like that. All right, questions on that?
I don't really understand what we did. How did we jump from that fraction to just having the 1 minus x to the n?
All right, good question. Sorry about that. This part right here, we're going to use the fact that the sigma, oops, that's embarrassing. We're going to use the fact that ax to the n, when you have an infinite series, is equal to this. Okay? But this x right here is not x in the problem. It's 1 minus x. So instead of x to the n here, it's 1 minus x to the n. It's just substitution.
Okay, that makes more
Do
sense.
you see it?
Yeah.
Because once you see it, it's going to be cake, I feel like. You just have to it's just all substitution. This whole section is all substitution. All right, so I'm going to pause here and let's just make sure we're doing this right. So I'm going to show you how to check this on your calculator. All right, so it's 3 over x. We did 3 over x. So let's go to Desmos. This is going to get crazy. Not really. It's just show you how to check it. I'll show you how to check it on your actual calculator too. But we have 3 over x here. Okay, this should be equal to Actually, with this, you can write the sigma as well. I'm just going to go to 10. I'm going to show you how to do this on your calculator in a second. And then it was 3 times, and we did 1 minus x. Oops. Button. The n. Now, if you notice, it's very strongly on a certain value, and then it kind of diverges away when it gets closer to the 2. It's not over here. Now, we only actually did 10 here. If I wanted to, I can do 100, and it's going to fit closer. It's counting it up right now. It's going to spit it out soon, hopefully. Oh, there it is. See how it sharpened it up a little bit? I think after 1,000, it overloads it. I don't know, but you can see it fits firmly on there. And you might be thinking, why is it only from 0 to 2? Shouldn't it be from, because this is 2 here, shouldn't it be from -1 to 1? Let me show you something really quick. So this is our R value, what we were talking about before, this right here. If you remember, for the actual function, it has to be between -1 and 1. Okay, it has to be between -1 and 1. That means this right here, this 1 minus x, also has to be between -1 and 1. Okay, I have to do a little bit of math here. This should be just some old school algebra. What I'm going to do is subtract 1 from everything. Okay, so I'm going to subtract 1 here, here, and here. And then you're going to end up with -2. This cancels. You have -x. And then 1 minus 1 is 0. Okay, but we want to solve for x. So what we're going to do is, let's do this color. We're going to divide by -1 here, divide by -1 here, and divide by -1 here. Now, if you remember, when you have inequalities, if you divide by a negative, you have to flip the sign. So now you're going to end up with 2. This sign flips. This is x. And then 0 divided by anything is just going to be 0. So now you end up with 0. You end up with the interval of convergence. This is called the interval of convergence. Instead of -1 to 1, it ends up being 0 to 2. Okay, and it's solved the same way. These problems don't ask for it, but on your quiz, it'll say write f of x as a power series, and then it'll say, I'll write it in now, find the interval of convergence. Find the interval of convergence. To find the interval of convergence, all you have to do is take whatever the base is, this, set it between -1 and 1, and solve. This one's already solved for, so technically the interval of convergence is right there for this one. This one, same thing. Oops, let's do a different color. It's between -1 and 1. This one is between 0 and 2 because we went 1 minus x this time, so it had to shift everything. Okay, and I can show you this first one, 1 plus. I can show you what it's going to look like. Let's bring it down to 10. This was an alternator times x to the n. If you notice, between -1 and 1, it matches up perfectly. As soon as it gets closer to the 1 or the -1, it diverges, but it converges between those two values. Okay, I'm going to show you how to do this in your calculator so you don't have to do it with Desmos. Okay, so let's go to our calculator. Let's clear this out here. All right, so what you can do is we graphed 1 over x. All right, and then we want to do math 0. And we are having x. Actually, we have to do n now because we need the x in the equation. So 0 to, let's just say 10. I don't know actually how long this is going to take for this one. And we're going to do 1 minus, hold on one second. I did this wrong. All right, so we're going to do -1 to the n. I'm going to fix it. I realize I wrote y1 is incorrect. Parentheses times x to the n. All right, and then we go up here, and I hope this works. 1 plus x. All right, graph it. I'm also realizing if you don't have a color graphing calculator, this might take a little bit longer. Yeah, 10 might be too much for this calculator. Desmos has the power of the internet, or this thing does not. Oh, no. Oh, there it goes. It just took forever. And that's not even right. Hold on 1 second. Oh, because I didn't do parentheses. This is embarrassing. Don't laugh. I'm embarrassed. Here we go. Now we're cooking with gas. Now I got to get rid of this thing here. Oh, okay. Here, I'm going to show you a quicker way of doing this. This should work better. If you hit window and change XRes to 8, I think it graphs faster. So if I hit 8 here, it might graph real quick. No, never mind. It gets it all messed up. Dang it. Sorry. This just takes a while. Maybe if we lower the 10 to something else. Let's try 4. Nope. Dang it. I mean, you could see it overlaps, but I want it to be a little bit smoother. The XRes is the resolution, so it's messing with the resolution a little bit. That's why the graph's getting a little... All right, so we're going to have to wait a little bit now. This is no fun. Is anyone working on their calculator?
Yeah, it's working on mine.
Yeah, it's weird. Like this emulator on the calculator, on the computer, I'm sorry, it goes actually slower than the real calculator, which is weird. You think it'd be boosted. But long story short, you can check a little bit, I guess, on this if it just takes a little bit. Here we go. And you can see between -1 and 1, there's some overlap, and then it diverges after that. So that's how you do that. All right, let's go back to here. All right, here we go. 1 over x squared. Now, there are 2 ways to do this. The easiest way, which I advise doing the easy way, is to do it just like same as you did the problem before it, only instead of the x here, just make it x squared. So this right here, just imagine this as being x squared, and then redoing the entire problem with just x squared. And then now you have the answer. Okay, but I also want to show you a cool way of doing it that is way more work, but it could help you on other problems like number 5. So I'm going to show you number 4, doing it the longer way, but it'll make sense when we get to 5. We can't do it for number 5 because it's an ln x. If you remember, that was one of the main things we're trying to figure out today is what is this as a polynomial? So I'm going to show you number 4 doing it this kind of a weird way. Okay, but again, it's just for the lesson. I would not expect you to do it on a test this way. Do it the simpler way, where it's 1 minus something. Okay, here we go. What I'm going to do is I know that the derivative of -1 over x is equal to 1 over x squared. So if I did the derivative of this right here, it ends up being -1. So I bring the -1 down. It's -1 because there's a negative already there. Right there, x to the -2. Okay, so if I simplified this, it would just be x to the -2, which is 1 over x squared. So this is perfectly legal what I did. Again, do I expect you to do it this way? No, I'm just trying to show you for illustrative purposes. Okay, I would highly advise understanding
Your mic.
this. Oh no, okay, hold on. Cool. Can everyone hear me?
You're good.
All right. Sorry about that. Thank you, dude. Appreciate that. All right. So 1 over x squared. So that means the derivative of negative 1 over x is equal to this. Well, what's crazy is we know what this is right here. This 1 over x is as a summation because it's right here as a power series. That's equal to that. Okay. Well, it's only equal to, hold on, not the 3. Ignore the 3. It's equal to this part. So what I'm going to do is I'm going to substitute that in. So I'm going to rewrite this and with that substituted in. So I'm going to say the derivative of negative, and then I'm just going to rewrite, well, that's a terrible sigma. I'm going to rewrite that up there. To be something like this. Okay. And I'm going to show you how to do this derivative here. Okay, so I just rewrote the green right here, made sure there's a negative in there so it matches. And I'm going to show you how to do the derivative of a sigma. It's the same rules of what you're used to, so it's nothing new. Okay. Now the derivative is with respect to x, so the main thing we need to worry about is the x. The n's, all that other stuff is just a constant. Okay? It's constantly changing from 0 to 1 to 3 to 1 to 2 to 3 to 4 to 5 to infinity, but you can still treat this just like a regular number. Okay? So it's going to be negative because of this negative right here. So act like we're doing the derivative of negative 3x squared. Doesn't really matter. Okay? The negative would stay in the answer. You need a negative 6x. The negative's still there. So we're going to keep the negative. We're going to keep the summation because the derivative doesn't do anything to the summation. The summation's with n. The derivative's only with x. Everything else, just you don't have to worry about. Okay. Here, we have 1 minus x to the n power. Well, imagine if I said, what's the derivative? Hold on. Let me delete this. But imagine if I said, what's the derivative of 1 minus x squared? You should do this derivative in your sleep. You should be able to do that, no problem. That was covered in Calc 1. Let's just say that you forgot Calc 1. I'm just going to do a quick review on this. This is the outside layer, so you bring the 2 down. Everything else stays the same, but you have to minus 1 from the power. So this layer is gone. Then you have to multiply by this derivative here. The derivative of that is negative 1. So you end up with final answer of negative 2 times x minus 1 to the first power. Okay? That's what happens when it's a 2. You bring the 2 down. Here it's an n. But you do the exact same thing. You bring the n down. You bring the n down. You minus 1 from the power. And then you multiply by the inner derivative, which is that negative 1 again. And then that's the answer. Oops, I should simplify it. The negative and negative should be simplified. Hold on. Plus, plus. And you end up with the final answer of, I hate rewriting all this stuff, but I have to do it. N times 1 minus x, the n minus 1 power. Final answer. Should just circle it. So I'm doing the exact same thing I was doing, only this time I'm using the fact that there's a derivative that you can use here. The next one we have to use an antiderivative. That's why I'm showing you this derivative one first.
What I don't get is what led up to us actually having us do a derivative. Like, why did we have to do that?
You didn't have to. The reason I wanted to show you that you can do a derivative with this, but you don't have to. If you wanted to, you could do this like the same old way that we did this. Oops. That we did this problem here. We could have done it the exact same way. So it was basically the only reason why was because the only reason why was because I was just trying to show you this. That's all.
Would you be able to do it that other way?
Yes. Here, I'm really quick. I'm going to show you how to do it the old way that I just did it. You basically the way that I did it up here. So basically, you would rewrite it as this, right? Because it's equal to this thing right here. So now what you would do is you would say this, it's equal to the summation of that right there to the n power. This is actually the same thing, believe it or not. It doesn't look like it, but it is. These are the same things. So I did this in 2 steps. Here, I had to show you with the derivative. The reason I'm showing you with the derivative is some of the problems on your practice problems, it says using differentiation, find the power series. That means you have to use the derivative. For number 5, you have to use the antiderivative. There's no other way of doing number 5 unless you have an antiderivative, because you can't get ln x any other way. For 4, you can, because you just did it this way. You can do it this way with number 4. You can't do that with number 5. Okay, there's no way of turning that into be 1 over 1 minus x. This 5 cannot look like home base, so we have to make it look like home base somehow. So you have to understand how to do number 4 and number 5. It's the same rules that we're used to. It's just now instead of squared, it's an n, and you have to bring the n down. If you wanted to as well, you could have done this, which this takes a lot more time, but it's kind of easier to see, I guess, maybe, is this part right here, this orange. If you just look at the orange, you can write it out as a summation. So you can do 1 minus x to the 0 plus 1 minus x to the 1. I factored out that negative one, that negative right there, just so I don't have to worry about it. This way does take longer. 1 minus x to the 3rd plus dot, dot, dot. Okay, all of this right here. Now what you can do is just do the derivative of each one of these. Okay, this is equal to 1, so its derivative is 0. This derivative right here is negative 1 plus, bring the 2 down here, do the derivative times negative 1 plus this derivative right here, 3, 1 minus x to the 2 times negative 1 plus dot, dot, dot. Now, if you write this out, now you'd have to write this out as a series with summation. It would be sigma n equals 0 to infinity. Hopefully you see that this is negative, so that becomes positive each time with that. And also this all has to be negative anyway. I forgot to put the negative 1 in there. So there's the negative there. And then we want 0 for the first one, so we can ignore that one. This first one, so they're all negative. So then they're all positive. Like, that's easy. This is the longer way. I shouldn't be doing it this way. But you end up with 1 minus x. That should be positive. To the n. Yeah, you end up with something like that. From that. And then if you do that, yeah, you bring the n down and you minus 1. So yeah, you end up with the same thing either way. The one thing is, yeah, forget what I was saying here, but you'd have to actually write it all out and see the pattern rather than doing it with the n's. But it's easier to just do it with the n's. And never mind what I was just showing. It's easier to look at this n right here and go, oh, that could be like a 2. So you bring the 2 down, you minus 1 from the power, and then you multiply by the inner derivative. Okay. Are there any questions on that? It's not easy. If I ever give you a problem like this and you can't see that the derivative of this 1 over x is equal to this over here, then just ask and I will tell you. But I don't think I'm going to give you one like this, to be honest. So I'll definitely give you something with like an ln x, though, because that's a little bit more involved. Let's do the ln x. Hopefully that tightens the screws a little bit more on this. Okay, we need this as a power series. Oh, I also forgot to do this, the interval of convergence on this one. It's still the 1 minus x that we have up here. So you can actually just rewrite the 0 to 2 for the interval of convergence because it's going to be the same. Whatever you used as the derivative, like you substituted this in here, it's going to have the same interval. If you wanted to, you could solve the interval. It's the same thing because it's that 1 minus x that we have here. So you still get 0 to 2. But all right. Oh, here we go. So hopefully you see this and go, oh my gosh, we can't this doesn't look anything like this thing right here. It has to look like this. It has to be like an a divided by 1 minus something, and it doesn't at all. But what we can do is we can use this derivative. Use the derivative for this because it's equal to 1 over x. Now, we did this 1 over x earlier, only we did it as 3 over x. But this part right here, this circled part right here in pink, is technically the 1 over x. It's this part right here. This whole thing, I should say, not just what I underlined. This whole thing right here. So what I'm going to do is rewrite it down here. So this 1 over x is equal to the infinite series from 0 to infinity of 1 minus x to the n. Okay. Now all I need to do is take the antiderivative of this. So if I take the antiderivative of this, you end up with a power series for ln x, which is weird because now you're making a polynomial out of a transcendental function. Okay, so let's do the antiderivative of this.
Do you need the negative on the... Wasn't it the negative of all that?
Oh, wait, yeah, was it? Wait, no, I don't have a negative up there. Was I supposed to have a negative up here?
I thought there was a... Or is it just 3 times? I'm sorry.
It's 3 times.
Okay, sorry.
Hey, no, good looking out. Good looking out, because I would make a mistake like that. Getting a negative. I think that's right. I did my Desmos, too, to make sure that there was no negative in that, right? Oops, let's do the Desmos. Hold on. I guess I didn't check this one. Hold on 1 second. Yeah, okay. Yeah, it's not negative. But either way, I love anyone that not interrupts, but tries to check me just to make sure I'm not making some mistake, especially since this is recorded. So I really like when people catch me right away. It is still 0 to 2 and there's no negative. Okay, sorry. I always assume you're wrong. That's like the good rule of thumb for these, for any math, really. All right, so I'm going to pull that out over here and do the antiderivative of this. This is going to get crazy. Not really. Same rules apply. So we're doing the antiderivative of this with respect to x. Okay, so if you wanted to, you could do, again, this is like a longer kind of way of doing it, but you can do the antiderivative of, let's just put a 2 in there. Okay, you should be able to do this antiderivative without an issue. Let's just do it together for fun. You could use u substitution, but know that this is linear here. So what you can do is just do the antiderivative as normal, and then multiply by whatever the derivative is of this inner layer, which is -1 plus c. So you end up with -1 minus x to the 3rd over 3 plus c. Now, if you wanted to do u substitution, by all means do u substitution. You get the same answer, but just know if that inner derivative is linear, you can just do this. It makes it easier. Okay. We're going to use this same principle here. If you notice, this goes up by 1. So it goes from 2 to 3, and then you divide by 3. Okay, so you divide by that same power. So we're going to use this principle on this problem. So what we're going to do is the sigma is unaffected by the antiderivative. So I'm just going to rewrite it. There's no x's in it. It doesn't matter. Okay. Now, when it was 2, it became 3. So when this is n, it's going to become n plus 1. It's going to be 1 more than it. The power is just 1 plus whatever was here. And it matches. The 3 and the 3 match. So I'm just going to match the n plus 1. Okay. I forgot the negative. Put that there. And then the plus c actually has to go in front. Oh, this is going to be crazy. All right. The plus c has to go in front. Otherwise, you're adding the plus c infinitely many times. So you cannot put the plus c in front. You'll see that in my answer keys. You cannot put it in front. Or, I'm sorry, at the end. You have to put it in the front. Okay. Again, if you put it over here, then it's adding it up infinitely many times in this whole problem. So you don't want to do that. Okay. And you can actually find the plus c on this problem, believe it or not. It doesn't seem like it, but you can. But first of all, is everyone cool with how I got this blue here? Any questions on that? All right. Now to find, so this is technically equal to f of x. Okay. Now what we're going to use is we're going to use a specific value to figure out our plus c for x. So we're going to figure out a specific value for x that we should pick. Does anybody have any ideas on which x we should use that makes our math very easy? Any ideas? Okay, we're going to use 1. Okay, because ln of 1 is equal to 0. Also, if you plug in a 1 for this x here, it's 1 minus 1 is 0. So you're summing up 0 infinitely many times. So that means you have c plus 0, because that, again, if you put a 1 in here, it's 0. So your c ends up being 0, so you don't really need it. So your final answer is just going to be this blue part here, which I'll rewrite for fun. Whoa, that's embarrassing. All right. And you end up with something like that. Now this is crazy to think about because you can now have a value, a function, a polynomial that represents this ln x here. And this is just a standard polynomial. Not standard, I mean, it looks kind of involved, but it's really just x's and you're adding stuff up. It's just that transcendental function, that ln x, you need infinity. That's kind of the gap. It's kind of bridging the gap between algebraic functions and transcendental is that infinity. Okay. Now I'm gonna show this on a calculator. It takes long on mine, so I'll just show you on this. ln of x, and it's equal to, again, we added 1 to here, and then we can divide by n plus 1. And then I need to make it negative before someone yells at me. Now, if you notice, that is almost fit perfectly between 0 and 2. I forgot to talk about that. The interval of notation is still the same as it was before because you use the antiderivative. It's from 0 to 2. It's actually, it actually includes the 2 this time, but we're not going to go over that until way later, that you actually include the 2. Because the 2 is actually, it's exact, but that's a whole nother ball game. If you notice, it does actually include the 2. It's when it gets off the 2 that it starts to converge or diverge. I'm sorry. It never goes to the 0 because the 0 goes to negative infinity. So if you're wondering, we're going to go over that later. Just for the purposes of this class, just know it goes from 0 to 2 and it works. Okay, and you can see it from all this right here. So if I made a function, let's just call it g of x, it was equal to, let's factor out that negative there, it's equal to 1 minus x to the 0, sorry, to the 1, it's 0 plus 1, divided by 1, plus 1 minus x squared divided by 2, plus 1 minus x. You'd have to go to infinity here. Hopefully you get the idea of what I'm doing here. As you can see, we're getting closer and closer. Let's get rid of this. You can see that it's getting closer and closer to 0 and 2. This one has 1,000, so I'd have to do 1,000 to be able to get it to look this crisp on this one. If it shows up, it takes a while because you're adding 1,000 things. Let's just do 0. Maybe that's faster. Back this thing up. There it is. So you can see the purple right there from 0 to 2. This one, again, you'd have to wait a long time. I can use my Python program, though, to get the rest of this stuff out there, too, but we don't need to worry about that. Any questions on what I did there?
So for these types of problems, we're going to need to find the interval of convergence for all of them?
Yes.
Okay.
And all you need to do is take whatever's raised to the n power, this part, just take it as going from 1 to -1. And the reason for that is based on what we went over here. 1 to -1, based on whatever that base is. It's from -1 to 1. Again, you don't need to know that. You do need to know that it's from -1 to 1, though, to find it.
Okay, thank you.
Mm-hmm. All right. And then with that, those are basically every type of problem I can think of. There are some problems where you can make it a little bit trickier by doing like partial fractions and stuff like that. I'm never going to give you one of those like that. They're all going to be similar to this type of problem that is right in front of you, as well as these problems right here that are on your final. There's an extra step here because if you notice, this 3 is not a 1. And home base states that it has to be a 1. 1 minus. It has to be a 1 minus on the bottom. But we need to turn that 3 into a 1 minus, which is not that complicated. I'm going to show you how to do it. We're actually going to do this one right now if that's okay, unless someone has any other questions. The main thing for this section is this right here, all of 613. This is what you have to do. This is part of the standard that I have to cover for the class. 611 and 612, there is no standard for that, so I cannot test on it. Supposedly, I'm supposed to follow those standards for assessments. This you need to be able to do. If you notice, I also made this 1 over 3 plus x, and this is ln of 3 plus x. I did that on purpose because your test is going to be, or quiz is going to be the same thing. You're going to have to use anti-differentiation or differentiation between the two steps. Okay, but it's good because you don't have to double dip. Or you can double dip, I should say. It doesn't matter. Okay, here we go. So we need to make this, let's just say this is our function, and it's equal to 1 over 3 plus x. Okay, we need to make that first number right here. This needs to be a 1 minus. Okay, so to make that 3 a 1, what I'm going to do is factor out a 3 on the bottom. So I'm going to factor out a 1/3 here. And you end up with 1 on top still, because 1 times 1 is still 1. 3 times 1 is that 3. Now, we still have that x that we have to take into account here, and it's plus x. So it's going to be plus 1/3 x, because this 3 times 1/3 x, because you're distributing it here, is going to be 3 times 1/3 is just 1x. So it's just basic algebra right there. But since you have it as a 1 plus, now you can make that into a 1 minus. We're going to do that the next step. The first thing I just wanted to do was the 1. Okay, everything is still perfectly legal. Everything still works. The orange and the red are equal. Questions on that? Okay. So this is equal to 1/3. Now I'm going to change this plus into a minus because you have to, because of home base. Okay, so now it's going to be 1 minus negative 1/3 x. So now it's a 1 minus here. This 1/3 is constant multiple. We can just keep it there and then deal with it later. But now we have that function that looks like that power series, that geometric series. Okay. This right here is your R. Questions so far? Everything's equal here, I think.
You lost me on that last step where you get the 1 minus a negative 1/3 x.
Oh, okay.
Did you do that again?
Yeah. Do you remember this one right here when I did the 1 minus minus because it's positive x and I needed to have 1 minus to match home base? Do you remember when we did this problem?
Right.
Oh, it's the same principle. But because it's a plus, a minus minus would make it a plus here. So this is technically equal. And the reason why we need it to be a minus is because that geometric series has it as a 1 minus. So that's why it's a minus minus. I mean, if you think about it, if you were going to simplify this, you would do this and this. You end up with the same thing here. You see how they're equal now?
Yep.
Does that help? Okay. Yeah, but that's the main thing is the fact that you have to get it to be a 1 minus to represent what we have for home base. Okay. The last step is to just rewrite it now. So now you end up with 1/3 drops down times, Now we're doing the summation. Remember, this is the summation of the geometric series from 0 to infinity. This is our r. So we're just going to do negative 1/3 x, and then it's just to the n. I mean, that's it. That's not the, I still have to do the interval of convergence part, but that's the power series for it. Okay, now what some people do, some books do, some professors make you do. I'm not going to make you do it. If you left this as the answer, I'm happy. But if you could have also rewritten this, you can factor out that alternator times 1/3 x to the n. Okay, that -1 and -1/3 x is the -1/3 x here. To me, this is simpler, the blue, but again, in the book, some of my answer keys, I do it the full way just in case I get yelled at by my boss and they want me to teach it a certain way. I don't care because personally it's the same thing. It does not matter. Whichever one you do. The interval of convergence, same rule applies for that. You just take whatever your r is, whatever this is right here. By the way, it doesn't matter if it's positive or not or negative, so I'm just going to make it positive because you're going from 1 to -1. So if you do a negative, it's just going to flip-flop these. It doesn't matter. You get the same answer. That's probably why people do it this way because it's already positive. I don't know. It doesn't matter. Long story short, you can make it positive here. Multiply everything by 3. And you get your answer. So the interval of convergence is from -3 to 3. And that's the answer. That's the full answer. Now say you wanted to check this on your calculator. It's just good to do it because you can see that interval, I feel like, a little bit easier. Three times. Okay, and then this is just going to be -1 to the n times over 3x. And I have to graph it. It should go from -3 to 3. Goes to 3 here, and then -3 is up there. This is -3 right here if you zoom in. Now it should work even with 10. It should still look pretty good. I mean, you can see it diverges pretty good at -3 right here, and then starts to do it at -3. But if you use your calculator and only do 10, it should still show it pretty well. These are not meant to be checked on the calculator, so that's part of the reason why I think this course is usually taught without a calculator, but I can kind of jimmy rig this a little bit to make it work. Okay, just for fun, I'm going to show you what would happen if you didn't actually take that alternator out. You end up with the same exact answer. Okay, you can see the purple and the red match up. So again, it doesn't matter. I accept either or. Questions on that one? Okay, the whole thing is you're making this equal to a polynomial, so it's easier to do some math on it sometimes. Within a certain range from -3 to 3. Beyond that, it stops working. We're going to go over that next class. All right, here, find the power series for ln of 3 plus x. Well, the derivative of ln 3 plus x is equal to 1 over 3 plus x. I did that on purpose. Your test will be the same way. Okay, so that means if I do the antiderivative of 1 over 3 plus x dx, it's equal to that ln of 3 plus x plus c. We have to figure out that plus c, but we're going to go over that in a little bit. So long story short, all we have to do is find the antiderivative of this thing right here. Okay, which it's probably easier to do it when the alternator's pulled out, but I don't think it matters. Let's just try it out. All right, so we're doing the antiderivative of this purple right here. So I'm actually going to copy and paste this. So I don't have to rewrite it. Sorry that you have to rewrite it. Unless you're doing this on a computer like me, but I doubt it. All right, getting rid of this really quick. All right, so we are doing the antiderivative of this because this whole thing right here is equal to this purple dx. Okay. You always have to have the plus c in front, so do c plus. Okay. The 1/3 is a constant, so we're not going to worry about that. The sigma stays the same because there's no x's in it. It doesn't get affected. This is with respect to x. Everything else is a constant, including this -1. This -1 is a constant. It's always going to be flip-flopping -1. It's not changing because of the antiderivative. The only antiderivative we have to do is this thing right here. Okay. So what you also could, well, we're not going to get involved with that too much. Okay. So what you could do is you end up with the 1/3 x, the n plus 1, and then we're, and then we're dividing this by, oops, I didn't do n plus 1. I said it, but didn't write it. By the n plus 1 like that. Okay, and then you have to multiply by the inner derivative here. In this case, it would be 3. So just multiply it by 3 to get the antiderivative. Okay, you end up with something like that. Let me check my work. Is there any questions so far? I think I messed something up. No, I think we're good. All right, so let's keep going then. This 1/3 and this 3 cancel, so that's kind of nice. Okay, we still need to figure out the plus c here. And to figure out the plus c, we're going to need to plug a certain value in to this right here, to ln 3 plus x. And the easiest value to probably plug in is 0, just because this right here ends up being 0 if you plug in 0 for x. Actually, I think that's the only value we can plug in because anything else wouldn't give us a 0 here. So if you say x is equal to 3 here, this whole thing's going to end up being 0. So you're going to have 0 plus c is equal to ln of 3 plus x. But x is 0, so I shouldn't have wrote x in there. I should have wrote 0. Or x is 3. Wait, this is embarrassing. This is supposed to be 0. Oh my gosh. Let's start it all over. Holy cow. Someone's got to chime in. I'm all over the place. Let's just delete this. Why did I say 3? I meant 0. Jeez. All right. X is equal to 0. So it's c plus 0, because this is 0. It's going to be -1 alternating with 0. Alternating 0 is still 0. Okay? The n plus 1 on the bottom, it's 0 divided by that, it's still 0. Okay? Is equal to ln of 3 plus 0. So in this case, your c is equal to ln 3. So your final answer ends up being ln of 3 plus all this orange stuff here. So it's going to take me a second to write it. Alternating whew. And you have, hopefully that's the right answer. Did anyone else get that? All right, well, we will check it just to make sure. Questions on what I did here? All right, let's do this. All right, so now the function is ln of 3 plus x. Okay, I'm going to get rid of that because I don't need it. Constant. This one needs to be multiplied by 3. This one ends up being plus 1. Oops, that's right. This Moses weird about that. This one is divided by n plus 1. I could have made the whole thing a fraction too if I wanted. Move this over so you can see it. This 1/3 and the 3 cancel. Let's delete that. So you have something like that. Now, if you notice, there's a shift that's off a little bit on this, and that's where the ln3 comes into play. And now you can see it fits on it perfectly. It's also between, this one's between -3. Oh, I only went to 10, but it is still -3 to 3. You don't have to redo it. It's the same one as the one we just used, -3 to 3. And you should be good to go. So that is the answer. I didn't do the interval of convergence. I can do that really quick. So the interval of convergence is just going to be -3 to 3 again. Technically, it actually equals. It works at 3, but we're going to go over that later. We're not there yet. We are not there yet. All right, questions on this? Questions on anything? We went over a lot today. All right, make sure you know how to do derivatives and antiderivatives using the series for your quiz. If you do have questions on any of that, definitely let me know. If you have questions on the quiz or anything like that, let me know too. I do have to leave soon because I have to close on a house, but I got time. So let me know what questions you got or what you want to work on. Whatever you want to do. Practice problems, whatever you need. Everyone's leaving.
Here, I'm going to ask one question. So,
there we go.
So could you quickly go over for me again why we use antiderivatives and derivatives, or derivatives and derivatives
All
for
right,
solving some of these?
The main reason why is the only way to get it to look like this sometimes the only way to get it to look like this is if you do a derivative or antiderivative. So we're simply using the derivative and antiderivative to make this look like it's that geometric series, that a over 1 minus x. So you have to get it to look like this. And ln luckily does that with its derivative to be 1 over something. So that's the only reason we use integration or differentiation, is to make it look like this. This other problem right here, we did not need to do that. I just did it to show, like just for an example purposes. But this one you had to. There's no way you could have gotten this to be 1 over something because it's an ln x. You just can't do it.
Okay, that makes more sense.
I mean,
I
if you
don't know,
try
it was, I think I just need more practice with it. It was just like brought up out of nowhere, and I was like, what the heck? Where's this coming from?
I'm sorry about that. Yeah.
No, you're good. You're good.
It's just to make it look like that home base. And now some problems can never look like home base. For example, sine x. The next class we're going to go over like how do you turn sine x into a polynomial? Because it doesn't become a 1 over something like ln x does, like 1 over x. There's another thing we're going to do that I'm going to show you. So.
Okay, I think I got it.
Yep.
Thank you.
But that's the main thing, is turning it into, if you have trouble with it, like on a quiz, I would give you a hint. I'd be like, well, if you try doing the derivative, I would try to point something out to you to help you. But
okay, cool.
Usually these quizzes are one of the highest quizzes because there's usually only 2 problems. Like literally it'll be like 2 problems like this, and that's it. I'm not going to give 5, and there's nothing like 611 and 612. Again, the only thing you need to know about 611 and 612 is the definitions of converge and diverge, and then you need to know this. This is the main thing you need. I mean, it is a really weird fact that if you add up things that increase in power, it ends up equaling this. I mean, it is, so just kind of just using facts, I guess. Oh.
But yeah, okay, cool. Have fun closing.
All right, thank you. I'll try. Peace out.
I had a question about my quiz.
Yep.
So like on mine, you wrote that like I only sent you 1 page.
You sent me 2 pages, but it has to be 1 pick. It has to be one picture.
Oh.
It doesn't matter. You got everything right. I
Yeah.
just it's just easier to grade. Like, so if you notice, like the graded quiz that you have, it's missing that other page because it takes me a while to like put everything together. Like I can show you right now. Like it literally is a nightmare to like put it on there and copy and paste it and put it in there. And like that's why it's just easier if people take a picture. That was one thing. But your work was beautiful for 4. So like if you look at your own work, you got an A+ on it.
Oh yeah, I was just curious if like you gave it to me because like the extra credit, but that's cool. If it was right, then it was right. That's cool.
No, yeah, you got it. You're all good. Yeah, very, very good quiz. Very easy to grade. Like I'm actually going to start giving extra points to people that are so neat because neat. The only thing you're probably going to ever take out of this class, anyone, is like the fact that you're neat and you're like doing thinking. Like you're going to forget all this math. No offense, not you, anybody will forget all this math. So like, I don't know. I feel like neatness is an important thing for life. So I very much appreciate your test. It was just had to be on one picture. That's all.
Okay,
So,
got it for the future. Thank
Yep.
you.
Yep, no problem.
Okay, bye.
Bye.